we looked at an experiment before where we had to find out the majority charge carrier concentration. How do we measure the minority carrier concentration? So for this, we do what we call as Haynes-Schockley experiment. So what we get in this experiment is we find the independently measure the minority carriers, mobility, mu, and diffusion coefficient. So we have to remember this is in contrast to Hall effect. In Hall effect, we used resistivity to obtain the majority carrier mobility, and Hayes-Schockley experiment, on the other hand, is used to measure the minority carrier mobility. The experiment is simple. A pulse of holes is created in N-type bar. So this light pulse which is falling here will create these holes in the system, and there is already a current flowing, so it is under an electric field. Now this pulse will start traveling from this side to the right because there is an overall electric field applied to this bar. Now the pulse itself is drifting in the field. So if there was this high pulse here, this is now moving after time t1, t2, it keeps on moving to the right hand side. And while it's moving, it's also going through diffusion also. So it's spreading out because of diffusion. So what we can do is we can measure the excess hole concentration at any point down of the bar on the right hand side. When we do that, that can tell us exactly how much has been the spread of the pulse, and what is the time that's required for holes to drift a given distance, and that will give us a measure of the mobility. And on the other hand, the spreading of the pulse during a given time will be used to calculate the diffusion coefficient. So in this figure, what we see a pulse of excess carriers at x is equal to 0. We take this as x is equal to 0, and here n naught was very higher than p naught, so because it's n type. But when at t is equal to 0, when the light pulse strike the bar, the electron change was small, but the hole concentration change was significant. So once that happened, the excess holes started drifting to the right hand side, and they reached x is equal to L after some time. Now the holes are monitored at this point x is equal to L, and drift time is what we write as TD, and that is used to find the drift velocity Vd in this case. So we have drift time Td, and that's used to find the velocity, drift velocity Vd. So from this we can find then mu p, which is Vd over electric field. We have seen this also before. But now what we are doing is, with this experiment, we are doing this only to find the concentration of minority charge carriers, holes in this example. So Haynes-Schockley experiment measures minority carriers mobility in a very straightforward manner. And unlike Hall effect, which gives us the majority carrier mobility. Now, there is a few equations which basically tells us that it has a Gaussian distribution, which is the kind of distribution what we see, that there is a center maxima and then they are distributed on either side, and the distribution keeps on increasing when they travel. But these equations in this rectangle are the important ones to remember. You know those already from before. Now there is another thing that we want to measure, is that what is the diffusion coefficient using the shape of the this minority hole concentration. So this is the relationship that's ultimately used to find that. So delta x is how far is that value from that center point, and TD is again what we have seen here, we call this as the drift time. How long does it take for the charge carriers to drift? Now using that we can find out what we call as diffusion coefficient. So in an experiment, delta x would be given because we would want to find out, for example, there is example 4.5 given in the book. Again, we are given the delta x in that example. So it cannot be measured directly. So we use this experiment to find that, and delta x is equal to this is the distance. So if you have the equation, so basically this L is delta x. Let me write it down. So this is what is delta x, the diffusion length. So how far it has grown from that center position where the introduction was of light was done. So now this would be something which gives us the concentration of majority carriers in a given minority carriers in a given system. Let me, I think I need to correct this one. So from this relationship we have delta x, which is equal to delta t times Vd, that how long we take to measure. And from this relationship, so delta t times L over Td, that's how we define delta x. It is not just L, but this is the time it took for us for that dispersion to occur times L over Td. That's how we would measure delta x. So now this is something what it gives us the concentration of minority charge carriers. All right, so now this is an example of how we would use this example 4.6, where we are given the length of sample, we are given the field that's been we're given the voltage that's been applied. So field would be E naught over the length, which is given here. Now here again we are using centimeters. Now a pulse arrives at 0.2 after this time, after injection. So we are taking these numbers to find mobility first, and then we are finding the diffusion coefficient.